Bismillah ar-Rahman ar-Rahim. So today we will go through the paper 6 ATP from March 2023 for IGCSE 0620 chemistry. Let's get started. Zoom in. So long chain alkanes can be broken down into shorter chain alkanes and gaseous alkenes. Vapor from long chain alkane is passed over a very hot catalyst, and the gases formed are collected over water. The apparatus used is shown in figure 1.1, right? So you've got long chain alkane on mineral wool, aluminium oxide catalyst, delivery tube, water, and you've got gaseous alkenes. So what is the apparatus labeled A?
Wait. Trough?
Yes. You can either call it a trough or a water bath.
Okay.
The catalyst is small pieces of aluminium oxide. Explain why several small pieces of aluminium oxide speed up the reaction more than one large piece of aluminium oxide.
Wait, let me think. Because, can you go back to the question? Yeah. Does this something have to do with greater total surface area?
Yes. So you can say larger surface area is available. Name the item of apparatus that can be used to heat the long chain alkane and catalyst. So what are you going to use to provide heat?
Uh, Something with it was some type of burner.
Yes, but they want the exact, right, the proper name. So it's a Bunsen burner.
Yeah, I had this in mind, but I did not know like how would I just say it without pronouncing it wrong.
All right, add two arrows to show where the apparatus should be heated. So you need two arrows. Where are you going to provide heat?
One underneath the catalyst,
Okay.
and wait. One under the long chain alkane.
Right. So it's soaked in mineral wool, or the mineral wool is soaked in the long chain alkane. So we're going to provide heat to cause it to vaporize. Right. So the heat being provided over here is to vaporize the long chain alkane. Right. And so those vapors are going to travel to the catalyst, and you're providing heat at the catalyst to as activation energy to cause the breakdown into shorter chain alkanes and
Yeah.
gaseous alkenes. Okay. So the gas collected is tested using aqueous bromine. Alkenes turn aqueous bromine from orange to colorless. When the first few bubbles of gas are collected, the aqueous bromine does not change color. Explain why the aqueous bromine is not changing color initially.
Mm, Let me think. Wait.
Right? They're talking about the first few bubbles. So just when the bubbles are forming.
Okay. Let me think. Is it because it's most probably air?
Yes.
was
So
oxygen inside.
this is not a vacuum setup, right?
Yeah.
And so there's air. So when you're heating it, the gas is being pushed, and so whatever air's in the delivery tube and the test tube over here, that's first going to be pushed out, right? And so
Yeah.
all right. As soon as the experiment is over and the heating is stopped, the delivery tube must be removed from. This is a repeat question. Now, if you do enough papers, you will realize that there are certain questions that are always asked, certain concepts that are always tested.
Yeah.
If you remember, we did this in the specimen as well,
I think I do remember vividly.
right? So if you have these concepts clear, you're like, yeah, just quickly answer it, and that's it. So, right, the delivery tube must be removed from the water as soon as the heating is stopped. Explain what happens if the delivery tube is not removed from the water as soon as, right? So the focus is on not. You're not asking why it is removed. You're asking what would happen if it's not removed immediately.
A suckback occurs.
Okay, so that's one point.
It's like a phenomenon. So okay. And do we need the consequences?
Well, you need another point. So what do you suggest?
Uh, let me think.
I mean, because this you're not being tested for grammar and English, this is fine. Otherwise, to put it more accurately, water will be sucked back into the delivery tube, right? But yeah, this is not an English paper, so
Yeah. Okay. Acha, okay. There will be a partial vacuum inside the apparatus.
how is that going to cause a problem for us?
Yeah. Okay. No. No. The sudden temperature change can cause a problem.
Okay, you're on the right track. So, right, the water is obviously not hot, right?
Yeah.
Comparatively, it is much cooler than the test tube or the boiling tube that is being heated. So you're providing is
Yeah.
that, so
So when
this
the
thing is
cold
hot.
water. Yeah.
So
So it
when
when
the
it gets.
water is sucked back, the delivery tube is
Yeah.
fine.
Yeah.
But
Yeah.
when it's sucked back into the tube, the sudden change in temperature from hot to cold will cause the tube to break or crack.
Yeah.
All right, so that you can either say test tube or what's it called?
It will shatter.
No, boiling tube, right? It's the either of the two. So the test tube, boiling tubes have like they're wider and bigger as compared to test tubes. Test tubes are narrower, right,
Yeah.
and shorter. So the test tube, because they haven't specified which one it is, you can use either the test tube or the boiling tube. Will you can either say break or crack.
Okay.
Again, if you want, you can give a reason due to sudden. It's not required, but as I've told you, give as complete an answer as possible, keeping the marks in mind, right? You don't want to write an essay out of this, obviously.
Yeah.
Okay, next question. A student, wait, we will have four of these, right? Just three? Four. Okay, let's do this. So, lots of text over here. A student investigates the solubility of ammonium chloride in water at different temperatures. The student does 5 experiments using the following instructions. So, initially, experiment 1, fill a burette with distilled water. Run some of the water out of the burette so that the level of the water is on the burette scale. Use the burette to add 8 centimeter cube of distilled water to a 5.25 gram sample of ammonium chloride in a boiling tube. Clamp the boiling tube at an angle as shown in figure 2.1. So you've got solid ammonium chloride, you've got water, right? It's at an angle clamped to a stand. Gently heat the bottom of the boiling tube while stirring the contents with a thermometer. Stop heating as soon as all the solid has dissolved. Continuously stir the solution with a thermometer while it cools. Measure the temperature of the solution as soon as the solution becomes cloudy and a solid starts to form. Okay, did you follow all of that?
Yeah.
All right,
Yeah.
because yeah, lots of text. So experiment 2.
Damn.
Use the burette this time to add 0.5 centimeter. So initially you used 8 centimeter cube. Now you're using 0.5 centimeter cube of distilled water to the mixture in the boiling tube from the previous experiment. So all of this continued on to experiment 2. You're adding half a centimeter cube. Clamp the boiling tube as shown. Gently heat the bottom of the boiling tube while stirring the contents with a thermometer. Stop heating as soon as all the solid is dissolved. Continuously stir the solution with the thermometer while it cools. Measure the temperature of the solution as soon as the solution becomes cloudy and a solid starts to form. So basically repeating everything. The only difference is you took all that you did, you didn't throw it away, you added another half centimeter cube, you did all of that again. Experiment 3, repeat experiment 2, right? So you're going to add another half centimeter cube. Right, so over here we are at 8.5. All right, make notes on your paper. This is 8.5 centimeter cubes in total. Now you're at 9 centimeter cube in total. Another 0.5 over here. So now you're at 9.5 centimeter cube. And another 0.5 over here. Right, and so now you're at a total of 10 centimeter cube. Okay.
Okay.
Aram, are you following? Yes. Okay. Use the information in the description of the experiments and the thermometer diagrams to complete table 2.1.
You might want to zoom out a little for this.
Yeah, just a sec. Can you read,
Yeah, I can read.
or is this better? Okay, so in first they're asking what's the mass of ammonium chloride used in these experiments. So if you go back to the instructions, right, the only time you're adding ammonium chloride is 5.25 grams, and you're using that same amount in all the experiments, right? So the mass of ammonium chloride is going to be 5.25 for all the experiments. You're not adding anything above that.
Yeah.
Okay, so don't be like, no, it can't be the same, right? Our kid logic should not be applied over here, right? Total volume of water, we just did that. Right, now we need to write it down, and so it's 8, 8.5, 9.0. Remember 9.0, not just 9, right? 9.5 and 10.0. Thermometer diagram when the solid starts to form, and now you need to take a reading. So for this I'm going to zoom back in. What's the reading on the thermometer?
Yes.
17.
No, each line is 1 degree centigrade, and if it's falling between two lines you can estimate up to 0.5 degrees centigrade. So take a look again.
78.5.
Yes. Now, see, I'm not putting any units over here because the units are given as the headings of these columns. Okay, and if you're ever asked to make a table, you need to make a table like this, right? So you need to have everything properly labeled with the units, and then you're writing up to, right, 2 or 3 significant figures, right, 2 decimal places, very much like properly. Okay, next reading. What's the next reading?
67.
67. Right, so this will be 67.0.
Is it
Next.
important to write 0 after that 0?
Is it important to write 0? Yes, because that 0 will count as a significant figure.
For volume as well?
Yes. Right. So you can see I've written 9.5 and 10.0 and all, right? So you'd say, okay, 9.5 makes sense. But why 10.0? It also shows the degree of accuracy, because you're using a burette, and burettes are used for accurate volumetric measurements.
Yeah.
All right, next reading. This is easy, obviously.
60.
Yep. So again, 60.0. Next,
53.5.
53.5. And lastly,
46.
49.
46,
49.0.
49. Yeah. All right. Now, making a graph out of this. So complete a suitable scale on the y-axis for temperature and plot your results from experiments 1 to 5. Draw a line of best fit through your points. All right, so this is the volume of water starting from 8 going all the way up to 11. Right, and so the temperatures that we have are going up till 78.5. So 30, 40, 50, 60, 70, 80. We can do that. So we can do one large square is 10 degrees centigrade. So this is 40, 50, 60, 70, and 80. Do you understand how I just quickly figured out what scale to use?
Yeah.
No. I mean, yeah, there's a 10 degree difference. So yeah.
Right, so they've given you a starting point, and what you're noticing over here, right, neither of the axes is starting at 0. What
Yeah.
we're taught in our younger classes is that the axis needs to start at 0. That's not true.
Yeah.
That's not true. Okay, and the scale of the axis, both the axes can be different. Right, so over here, one big square, so that's 10 small squares, is equivalent to 0.5 centimeter cube. And over here, I'm taking 10 squares to be 10 degrees centigrade.
Yeah.
Okay. Now, how did I figure that out? Well, I just saw how much space I had. Right. So I had 1, 2, 3, 4, 5. I can go all the way till the end. Right. Also, there's no rule that you can't go all the way till the end of the graph. You can. And I saw, okay, fine. We're starting at 30. Right. My readings grow from 49, which is the lowest reading I have, all the way up till 78.5. So I need a temperature of up till at least 80. Right. So,
Yeah.
so yeah, I went all the way up. Can I manage that? I can, right? 40, 50, 60, 70, 80. I'm not skipping any numbers. There's a 10-degree interval. And so I can go all the way up till 80 till the end of the y-axis. And this way I'll be using the majority of the graph. I could have taken a smaller scale, right? I could have done 30 and
35.
no, meaning 50 and then 70 and then 90. But then, my graph would have been limited to this portion only, right? I'd be using less than half the graph,
Yeah.
right? And I want to use the maximum area possible, right? What's suggested is about 75% of the graph area, right? Technically, I believe it's slightly different given the syllabus. I don't remember it off the top of my head. But yeah, what's suggested is to use 75% of the graph area. Okay, now we need to plot the point. So the first point, right, for the 8 centimeter cube one is 78.5. And so, right, in an actual exam, you'd be leaning really close to the paper to count the boxes. Right, I'm just zooming in. So that's 75, 6, 7, 8, 78.5 should be all right. I need very fine marks, so I need to go to 0.5. Hey. Why is it not respond? There you go. Okay. So once again, at 8 centimeter cube, this is 78.5. So make a very delicate cross. Then you have 8.5 centimeter cubes is 67 degrees. So 8.5 is here. And what was it? 67?
Yeah.
Yeah. So 65, 66, and 67. And then at 9, it was 60. So that's over here. And then you've got 53.5 for 9.5. So that's 9.5 and 1, 2, 3 and 53.5 over here. And then 10 is 49. 49 up here. And right, they're asking you to draw a line of best fit. So right, that tells you it's not going to be a curve. Now best fit obviously meaning that it's not going to be going through all the points accurately, and it doesn't necessarily need to go through point 1 and point 2.
Yeah. Okay.
Right.
So yeah.
I believe this is somewhat a best fit. Obviously, right, depending on how students draw it, they're going to have slightly different results. And so whatever they're going to ask us to do next will right, be slightly different depending on. In fact, you know what?
Right. Right.
Just a sec. What if we do try making a curve out of this? I think that would be more appropriate. Does it look curvy to you this way?
No.
No?
Kind of in the end.
Obviously, that's not very good. This is
Yeah.
sort of like a limitation for me. Again, I'm not trying to go through all the points. Right? I'm going to go with that. It's not the best. Right? But let's see if our answers are anywhere close. Right? Now, obviously, if my answers vary,
So we can make it curvy or we can make it a straight line, right?
just a
Or
sec.
do we-
Just a sec. Okay, so no, it's not something that you go like, oh, I can do either a curve or a line, either works, right? So I go back and right, line, when they say line, it could be linear as in a straight line, or it could be a curve, because
Okay,
technically
depending on the
points, on the you see, you notice the trend, right?
yeah.
And you can notice the trend using the values. So if I just go up, right, you can see that there's no like linear correlation between, right, the difference in values is, this is like 8.5 of a difference, right? Well, no, 8.5 will go to 70 and then 3 more, so 10.5 of a difference. This is 7, right? This is another 17.5. No, sorry, 6.5. 6.5 of a difference, and then this is even less. So the difference is getting lesser, yes, but right, the increase in the volume is linear, right? You're linearly increasing 0.5 centimeter cube, but the decrease in the temperature when the solid starts to form is not linear in that case, right? You can see that. So you can sort of observe the values and try to figure out, and then you notice the points that you've put on the graph, and you say, well, is this going to make a straight line, or is this going to give me a curve, right?
Yeah.
Like, well, what's the trend of the values? And so you need to figure that, and that's part of the test. Now, if it's linear, right, what you can do is you can extrapolate. So you can extend the line that I initially did, right, and you can go all the way because it's linear. So whatever relationship is going to be maintained. theoretically. I mean, we know that there are situations where, right, a linear trend becomes non-linear, right? Or the other way,
Yeah.
yeah, it goes this way. So that also happens. So the extrapolation part doesn't always work. But don't do it for a curve, right? For a curve, just stick to the values in most cases, unless they're asking you, find the value at 10.5. Then perhaps you can try and extend it. So
Yeah.
again, the values we're going to get, the values that they're going to check whether you made the curve properly. And then whatever working you do, they haven't given any values in the mark scheme for this one. So they're going to check you based on the curve you've made, right? And so my curve isn't very proper, I admit that, but that's what I can manage at the time being. So let's see what we can work. The next question is, let me just go back to, okay. Now, like I just said, right? You don't normally do it, but the first thing they're asking you is extrapolate the line on your graph. So now, because they're asking you to do it, you extend it.
Yeah. Okay.
Again, as a rule of thumb, don't do it on your own. Now, since they're asking you to do it, you sort of notice how the way the curve's going, and right, you
Just
need,
extend along it.
yeah, extend it using that same like sort of curvature. Now, obviously, this is not proper. It's going to maybe something like that. I don't know. Again, right? Let's just go with it. Okay. So extrapolate the line on your
Are we gonna extend it fully, like touch the line?
well, if you don't need to, right?
Okay. But it would be fine if you just do it all the way, right?
You could.
Oh,
Yeah,
no.
you
Okay.
could. So extrapolate the line on your graph and reduce the temperature when the solid starts to form when a total volume of 10.5 centimeter cube is used. Right? Show clearly how you worked out your answer. So the first thing is you extend your line, right? And then you show on the graph that this is 10.5. So you make a dotted line from 10.5, right? And then you make a circle. Now it's going to be much finer than that. I'm not switching back. And then you go back, you make a dotted line. So not being too particular about this at the moment, you will have to be particular. So use a ruler. And so what I'm getting out of this is 1, 2, 3, 4, 5, 6, 46 degrees. Right? Now, as I said, the marking scheme does not give you a specific value because whatever reading you're getting depends on the curve that you've made.
Yeah.
Okay. So solubility in grams per 100 centimeter cube of water is calculated using the equation shown. Mass of solid dissolved times 100 over volume of water used. Use this equation to calculate the solubility of ammonium chloride in experiment 1. So mass of solid used was 8.25 grams multiplied by 100 over volume of water used was 8.0 centimeter cube. Are those the correct values? 5.25, 8. So what did I write? I wrote 8.25, right? So that's 5.25.
Yeah.
Right. What are we getting out of this?
Just a minute. One minute. Is it 62.5?
How are you getting 62.5?
We multiply 5 point. Oh, okay, no, wait. Like this. I'll do it again. 65.625.
Right, 65.625. Now here they've accepted a range of answers. They've accepted 65.625 as it is. They will be accepting 65.63 if you're rounding to 2 decimal places. If you're rounding to a single decimal place, it's going to be 65.6. They have even accepted up till 66.0 if you're just rounding it up to 2 significant figures.
Okay.
Right? But it doesn't hurt to be accurate.
Yeah.
Okay, describe how the solubility of ammonium chloride changes as the temperature changes.
Mm,
So again, if you take a look at the values, right, the temperature when the solid starts to form.
so
When there's more water, it can go to a lower temperature before it starts to come back out of solution, which means solubility is, right, how much solute can a solvent take, right, at a particular temperature, right? Normally for solubility, it's taken as room temperature. Right now, obviously 46 degrees is not room temperature, right?
yeah.
But what we can notice is as the volume of water is increasing, you can go to lower and lower values before the solid starts to come out again.
Yeah.
So what is this telling us about the solubility?
The story, when the ammonium chloride increases, the temperature increases as well.
No. Right? And overall,
Am I wrong?
huh?
Am I wrong?
Well, when you've heated it, right, none of the solid is coming out. It's only when the temperature falls that the solid starts coming out. That means in relation not to the volume of water, but in relation to the temperature, right, the solubility increases with temperature. And that's kind of a general rule for any solvent,
Yeah.
right? So the solubility increases with.
Temperature.
Do you understand the concept?
Yeah.
In this experiment, the volume of water was measured using a burette. State the advantage of using a burette rather than the measuring cylinder to measure the volume of water. This should be very, right, straightforward.
It is more accurate
Yes.
and precise. Yeah.
So the burette will be more accurate. State the advantage of using a burette rather than a volumetric pipette to measure the volume of water.
Hmm. It allows variable volumes.
Yes, so pipettes have fixed volumes. You can either say that, or you can say that you can add variable volumes using a burette.
Yeah.
Right? Pipettes have, or better yet to say, they measure fixed volumes. Okay, a total volume of 2 centimeter cube of water was added to the original 8 centimeter cube of water. Explain the disadvantages of adding 2 centimeter cube of water in 1 centimeter cube portions rather than 0.5 centimeter cube portions.
Mm,
This has to do with the results you're getting. So how will it affect the results?
uh, uh, adding like a huge portion.
Not huge. Just 1
Uh,
centimeter cube portions rather than 0.5 centimeter cube portions.
Okay, so adding 1.0 centimeter portion Wait. Does this result in fewer data points?
Yes, so you will have fewer results to plot your graph.
And I don't know what else comes to mind.
Right, and so your graph will be,
Less accurate?
yes. Suggest why it would not be possible to use 6 centimeter cube of water instead of 8 centimeter cube of water in experiment 1. So why won't you be using, or why won't it be possible to use less volume to start off with?
It might not be enough to fully cover
Cover?
the. No, might not be enough. Yeah. Honestly, I don't know this one.
So, right, the ammonium chloride might not dissolve properly. Or better yet, might not fully dissolve. Right, because again, right, solubilities they've given per, what was it, right, per 100 centimeter cube. So that's like a standard. So obviously, how much solute a solvent can take, like dissolve, depends on the volume of the solvent that's been used. If there's lesser solvent, then obviously it's not going to be able to dissolve as much.
Yeah.
Okay, we need to speed through the remaining 2 questions because, right, we don't have time. And in
How
fact,
many more questions do we have?
2, right, including the planning question. So let's go through this quickly. Right, student tests 2 solutions C and D. Test on solution C. Solution C is aqueous calcium nitrate, right? So they've told you that, and that's going to be CaNO3 twice. Complete the expected observations. The student dissolves solution C in, divides solution C into 3 portions. The student carries out a flame test on the first portion, right? So you go, they've given you the tests here at the end. There's a lot of blank pages.
Yeah.
And so, yeah, calcium is going to give you an orange red flame.
Okay.
To the second portion of solution C, the student adds aqueous sodium hydroxide dropwise until it is in excess. Right? So, what is the effect? So, using sodium hydroxide, aqueous sodium hydroxide, and aqueous ammonia is to test for the presence of cations, right? And so we know it's calcium. So we go back down,
White precipitate.
right? And not anions, cations, calcium. Effect of adding sodium hydroxide, right? You're going to get a white precipitate insoluble in excess.
Yeah.
So drop white is going to give you a white precipitate insoluble. To the product formed from B, so this thing, the student adds a piece of aluminum foil and warms the mixture gently. Any gas produced is tested, right?
Ammonia gas?
Yes. So, right, the test for the gas, right, turns damp red litmus paper blue. To the third portion of solution C, the student adds about 1 centimeter cube depth of dilute nitric acid, followed by a few drops of aqueous silver nitrate. What's going to happen?
Halide ions? Halide ions?
Halide ions?
It is a test for halide ions, right?
Yeah, so nothing's going to happen,
Yeah.
right? So no change. Good. So this is a test for halide ions. There are no halide ions over here, so nothing's going to happen. All right. Over here, we need to figure out what this is. So, right, table 3.1 shows the tests and students' observations for solution D. The student divides solution D into 4 portions. Use a glass rod to transfer 1 drop of the first portion of solution D onto a universal indicator paper. The indicator paper turns red. So, right, this means it is acidic. Yeah?
Yeah. Yeah.
To the second portion of the solution, add solid sodium carbonate, right? And so that's confirming that it's an acid, because acid plus carbonate is going to give you carbon dioxide gas. So it is confirming that it is acidic, or basically an acid. To the third portion of solution D, add about 1 centimeter cube depth of whatchamacallit, dilute nitric acid, followed by a few drops of aqueous silver nitrate. So again, this is a test for halides, no change. So no halide. So it's not hydrochloric acid. To the fourth portion of solution D, add about 1 centimeter cube depth of dilute nitric acid, followed by a few drops of aqueous barium nitrate, and you're getting a white precipitate. So what does that tell you? Right.
Just
Remember what this is used to sort of make?
could you zoom out so I can see the test one as well? Or like, you can scroll up a little. Yeah. Okay. Is it gonna be now? Okay. Is it gonna be 2? Maybe.
2? What do you mean 2?
It might be the
Okay,
pH solution.
this is just giving you information, right? So what we're doing is making notes while reading this. So let's see the question they're asking. Reduce the pH of solution D. So it's acidic, right?
Yeah, so it's gonna be likely between 1 or 3.
Right. So yeah, you can say, for example, 2.
Yeah. Exactly.
Okay. Identify the gas made. So right, that's CO2. Right.
Yeah.
Identify the 2 ions of solution D. So we know it's acidic. So one is the H plus.
And the second is sulfate ion.
How did you figure that out?
Guts.
I don't think guts will work over here.
Yeah, I mean, in Urdu, you can say it was a guess, honestly.
Right. So this test, right, what's forming over here is barium sulfate. It's given in the book. The insoluble salt, how to make insoluble salts, right? So that means that, right, you have the sulfate ion, right? And so
Yeah.
the acid you have is sulfuric acid.
Yeah, there's white precipitate written, so it would typically suggest chloride ion.
Chloride ion,
No, wait.
right? We tested for halides. There are no halides.
Yeah, okay. Okay.
Okay. Cadmium, cobalt, and vanadium are all metals. They react with dilute hydrochloric acid to form hydrogen gas. These reactions are exothermic. Plan an investigation to find the order of reactivity of the three metals. Your plan must make it clear how your investigation will be a fair test and how you will use your results to place the metal in order of reactivity. Right, you are provided with powdered samples of each metal, dilute hydrochloric acid, and common laboratory apparatus. What are you going to do?
Uh, we gotta check the temperature change.
No. Right, so they react with hydrochloric acid to form hydrogen gas. Right,
Yeah.
so the underlying concept over here is the more reactive,
Yeah.
right, the lesser the time it will take to produce the gas.
Yeah. Okay.
Right, if you're using the same amount, perhaps, right, so you can either measure the volume of gas or the time taken. So let's see. So first of all, you're going to use, right, what's the word for it, set volume of HCl for each test, so they're going to keep that constant. You're also going to use set mass of each metal. All right, so we're going to keep those two things constant.
Yeah.
Right,
Yeah.
then right, you're going to add the acid, not aid, acid to, in fact, you're going to add the metal to a test tube, followed by, right, HCl. Going to put in, like, you're going to put a rubber bung with a delivery tube into a gas syringe. You're going to connect a gas syringe to the test tube.
Okay.
Note the volume of gas collected after set time period. Right, so conduct the experiment first for cadmium, followed by cobalt and vanadium. Right, and then,
Yeah.
right, so you noted the volume of gas collected after a set time period. Right, and so the largest, right, the one that's producing, because the time is fixed, so the variable that you're measuring is the volume of gas. Right, and so the largest volume of gas collected is for the most reactive metal,
Yeah.
right? And lesser volumes will be for lesser reactive metals. Okay.
Yeah. Okay. Really, it's too much, but yeah, like I got it.
Well, that's how you're supposed to attempt it, right?
Yeah.
You're supposed to detail everything. So again, right, the volume of HCl used is constant. The mass of each metal used is constant. You add that, you connect it to a gas range, right? You collect the gas, right? And the time that you're collecting it for is also a constant, right? And then you repeat the experiments for like all three of them. And the one that has the most gas collected, because the time you're collecting it for is constant, right? And so within, like, for example, 2 minutes or 3 minutes or whatever, however long you're waiting, the most
Yeah.
gas collected means that that is the most reactive metal, right? Now, there are other ways you can do this experiment. If you take a look at the mark scheme, if I just take you to the mark scheme, right, very quickly,
Okay.
just a sec. Yeah. Google Meet has issues with Adobe.
Yeah.
Okay, so you can see over here, right, same known volume of acid, same stated concentration of acid, you could have mentioned that. Same known stated measured start temperature of acid, that's another thing you could have kept constant, right? Same mass or moles of metal. Now you only get a maximum 3 marks out of this, right? We're only getting 2 marks. That doesn't mean we're going to get 2 marks only, right? So you can only get a maximum of 3 marks for these. So they've given you 4 points, right?
Okay. Yeah.
So we got 2 marks out of this, right? We had the same volume and the same mass, right? Then
Yeah.
time until set volume of gas collected, or measure volume of gas after a set time. So we get our third, right?
Yeah.
And largest volume of gas in set time is most reactive.
Yeah.
Okay, and you're going to get marks for react metals with hydrochloric acid in a suitable container, right? Beaker, flask, test tube. So given all of this, I think we're getting 5 out of 6. So one thing that we should have mentioned is that not only the volume of the acid should be the same, but in that case, the concentration of the acid should also be the same in each case. So let's just go back and add that. So, right, otherwise you would have been getting 5 out of 6, which is not bad, but obviously we want to get our maximum score.
Yeah.
Right, and so if you missed it, you can add it to the end, right? You're like, oh my God, it's not in order. It doesn't matter. I mean, it's not like you make a mess out of it. It should be in order, but right, if you missed it, right, the concentration of HCl used should be the same, right? And you get your mark number 6.
Yeah. Okay.
And we're done.
Bye bye.
Right, and so that is the last class for chemistry. Right now, obviously, exams are just around the corner. Unfortunately, not in your case, but do keep practicing.
Yep.
Right.
Okay.
All right. See you around then, inshallah.
See you in the office.
Allah Hafiz.